The shape is the question, and we act as if we don't know the shape, except that it is solid and it is a body of revolution, meaning it has a cross-section that's round. And here we are, that's the ground level. And relevant is the fact that first of all, coordinates radial this way, vertical is z. The height of the root is, I call it L. And the question is this diameter, called the diameter at altitude z. That is the question. This function, this profile shape. And to make the analysis easy, we make this, by the way, you know that when things are on top of other things, then the pressure high is lower than the pressure below, especially when the body, in this case soil, is wet. So the pressure in the ground is higher than above ground. Above ground, the pressure is the pressure at altitude L. In the ground, it is higher, but to make life easier for the for the teacher, we assume that it is uniform, and it's called PG, meaning the pressure in the ground, which is higher than above ground. Now, what is residing inside this this root? You think, imagine a carrot, okay? If you've sliced a carrot, in cross section the carrot has it looks beautiful, okay? And here is the cut through the carrot. People in this field of study, which is called botany, the people have figured out that the so-called root is a bundle of tubules. That means very, very narrow little tubes that guide water, in this case, upward. You may think of a bundle of really, really narrow straws, like at Starbucks, you know. And obviously, water flows upward with great difficulty. It seeps upward. Seepage. And it seeps upward with an average speed called U. This U is like in fluid mechanics, the average speed in this body averaged over all these non-uniformities, meaning tubule and the solid. So that U is simply a number of whatever millimeters per second or smaller. And it is an upward speed driven with great friction upward by this pressure difference. The rate at which this movement upward is happening was figured out in the mid-1800s, and it is written this way. It is a factor called Kz divided by mu. I'll define very soon these things. And then the rate at which the pressure decreases upward inside the root. In other words, inside the root, at this location, the pressure is a function of altitude. In other words, there are three pressures in this drawing. There's the high one, in the soil, the intermediate one in the root, and the lowest one at the ground level. And this expression states that the seepage upward is proportional to the rate at which the pressure decreases from one floor to the higher floor inside this building called the root. Makes sense. This formula, this is the modern version of what is known as Darcy's law. Like the law of Fourier, this is not a law. In physics, it is the correlation that one gets from measurements. If you measure the pressure difference through packed sand, and then the flow rate through that packing, then that means you measure this proportionality factor that is spelled out in front with the viscosity of the fluid, in our case water, and then on top with this empirical factor, capital K should make you think of conductivity. In fluid mechanics, capital K means permeability in the vertical direction. So Kz is permeability. In Z direction. Okay? Now, Darcy was a mechanical engineer. His first name was, still is, but he's dead, Henri. And he was a graduate of the famous École Polytechnique. And he was working as an engineer in his home city of Dijon. And he was in charge of the water network in the city and also the display of artificial fountains that decorated the center of the city. And he wrote a book called The Natural Fountains of Dijon. And then, unfortunately, he developed tuberculosis and he died very young. But that's the story of something totally new from a person who, while busy doing engineering, kept questioning what was happening. So that's the flow of water vertical. The flow of water was also happening horizontally, coming from the ground into the root with a velocity, average velocity in this caret without structure called lowercase v. So the transversal velocity component, according to Darcy, is written as V equals permeability in the radial direction divided by the same viscosity. And then the pressure difference that drives the flow, which is Pg minus P at location Z, divided by the radius of the body of the root at altitude Z. Remember that capital D is the unknown. Okay? These days, these formulas can be derived by invoking Poisson flow through one of those little tubules. Because in Poisson flow, there is a proportionality between pressure gradient and flow rate through the tube. But Darcy was his own man. not a copycat. All right. So now comes the, just I was about to get the really interesting area. Now comes the a little bit of analysis. First of all, we will be answering the question of how good is this water pump? Meaning, what is the flow rate upward, which is m dot at ground level, m dot at ground level, which is the question, is equal to the cross-sectional area at the top, which is rho, and then pi over 4 d at the top to power 2, and then times the vertical velocity u at the ground level. And we'll get to it after we evolve the shape of the root so that this quantity is maximized when the pressure difference between ground level and between ground and above ground is fixed. So that will be the that unknown will be figured out, that function, after maximizing the production of water through the root. The analysis goes in a few steps this way. This is once again the root. And imagine here the difference between level z and z plus dz. And at this location, of course, you have p at location z. Can you see when I write this small? All of you? Okay. And then entering this chunk was mass flow rate m dot. Entering from the side is d m dot from the ground, from the wet soil, and exiting is the sum of the two, m dot plus d m dot. And of course, the chunk, which I'll draw bigger here, is populated by vertical flow u and horizontal flow v. dm dot is proportional to this v, namely v times the wetted perimeter, which is pi d times dz. So pi d dz is the lateral area, this area. And of course, the density of water. The mass flow rate, this m dot vertically is, I'll write it this way, m dot equals same sort of thinking, u, and then the cross-sectional area, which is pi over 4 d squared, and then the density of water. All right? So this chunk was expanded to look like this. And it turns out that if you if you combine these two, where am I? dm dot, I wrote dm dot here, and m dot, this expression here. If you combine them, so together, they lead to d, dz, and then d squared u equals 4 v d. That is what you get. Another, so that's the first of two equations that will give you the two legs on which to stand. The second equation, which I should have mentioned earlier, is that this struggle to find the shape is conducted while keeping the volume of the object fixed. So the volume, which is fixed, capital V, equals the integral from 0 to L of pi d squared dz. I think that's what it is. And yes. And so I'll put that in a square box, in a rectangular box, to mark this your position on the map of problem solving. Beyond this point, and once again, technique saves the day. You've seen more than once, most recently Monday, that because most of these ahas of design in nature end up looking like shapes that are shaped as power laws. The question about the shape that empowers you to maximize the flow rate upward, that shape would be a power law itself. So the question then is, which power law from an infinite number of possibilities? So we assume, and the reason why we assume is because we are not born yesterday. You've been in this course plenty, but you might have come up with this idea yourselves. We assume that the unknown shape would be of this type: d, some constant b times z to power m, where m is unknown. And then hand in hand with that, hint. Why hand in hand with something? Because you have two legs on which to stand, you see. So in addition to this assumption, you make the assumption that the local pressure excess, Pg minus P at location Z, we non-dimensionalize it as mu Kz here, is equal to another constant called A, and then Z to power n. See that? If we figure out exponent m, we know the answer to the question. Later, when we figure out exponent n, we will have meaning. M will tell us the shape of the root, n will tell us the flow rate through the top of the profile. And after this, I think you should be able to see similarities between this part of mathematics and what I've had on the blackboard last Monday. And because of those similarities, I will skip a few steps and tell you that if I substitute these two assumptions, I'll call them two assumed. I substitute them into the statements in the rectangles. So I put them here. Then I get two results. The very first one, you can do this yourselves. The very first one is that m must be equal to 1. So that's one thing that you get. The second result, because you've got two things to plug into, is that bn squared must be the same as, b squared n times n, b squared n times n, and n plus 1 must equal a constant called a kr over kz. By the way, the permeability to flow vertically must be greater than transversally. Think about tubules. They have a solid shell-like structure. So you should expect this Kr over Kz to be less than 1. These are two results that you get. And the rest is done in connection with them. If you substitute them into these expressions and then manipulate, you get additional results. In other words, let me just say that this expression in the bigger diamond is equation number 1098 in the book. The volume constraint is 10 and 88. And this I got that. I got that. And then if you substitute these two things into the volume constraint, those two things, the two diamonds, in the volume constraint, you get the requirement that b squared, L squared, no, L cubed must equal 12 over pi and v. So that's equation 1099. And you also get the, if you do the same throughout this panel, meaning going all the way down there, here's where I'm skipping, you get that the total pressure difference, Pg minus PL, divided by mu Kz must equal A to the power n. That's equation 10,100. And finally, I had erased the formula for the mass flow rate at the top. M dot L equals rho and then pi over 4, and then the diameter squared, diameter at the top is B times capital L to the power n. In this case, since n is equal to, I erased now, this becomes L and this becomes 1. So that means diameter squared means BL to power 2. And then Kz over mu, and then the pressure gradient at the surface, Pg minus P, the x, this is actually the pressure gradient transversally at location z equals L. Long story short, after you make all these substitutions, you get rho and then pi over 4 b squared a n, and then L to n plus 1. And finally, and I skip again, all of this leads to the expression for m dot L at the top. Looks complicated to recognize that the object of the game is a factor containing constants, multiplied by an expression that depends on the remaining degree of freedom, which is the exponent assumed in this second power law. And the question then is, how does freedom empower you to maximize the production of water? And the answer should be kind of educational, graphically, even before you do math. Here is the function that depends on n versus n. N is greater than 0. And let's see now, when n is small, so if Roman 1 means small m, n, that is small n, then this balloon goes as n to 1/3. So that's Roman 1. By the way, Roman 1 is correct in the small n limit. And Roman 2 is large n. In that limit, large n means n to 1/3 divided by n to 2/3 means Roman 2 varies as n to minus 1/3. So that means like this. Except that I made it decreasing because because of this minus, you see. Minus because it comes from the fact that in the large n limit, the denominator is greater than the top. Anyway, the point is that that's what you get. And that the real curve connects to the two tails. And you can get to the n of interest in two ways by intersecting the asymptotes. You get this result, obviously, if you say that Roman 1 is n to 1/3 is the same as n to minus 1/3. That means n equals 1. But you get the same result if you do the dn of the balloon and set it equal to 0 in this case. So in conclusion, you know everything about, first of all, about the shape, which means a conical root. But you also have this value for n, which if you substitute upstairs, tells you the rate of water production, and that rate is proportional to what you see up here. I believe that has to be L to power 2, and the rest is in the textbook for you to read. So the conclusion is that the root should be conical, and its water flow rate, when you substitute both the m and n equal to 1 into the expression for the mass flow rate through the top, you get that mass flow rate should be the same as the vertical permeability divided by nu, and then the overall pressure difference, and then 3v to power 1/3, and then pi and the ratio of the two permeabilities to power 2/3. What's important here is that the volume, the units are meter to power 3, represents the length scale of the root. For example, the length scale of the diameter or of the height of the root. So that is size in meters. And the lesson that you learn is that big roots, vehicle, big water flow rates out of the ground. Big trees with big roots are big water pumps. Big root, big flow rate.